Okay, good morning, and here is a blockbuster problem from matrix and combinatorics combined. If you'll see the recent trends in J Advanced, last 5 year question was having almost 3 to 4 questions of this type, and I have merged all the question and created a new one to give you the feel of how exactly we deal with problems like this. So S is the set. You must appreciate the set notation as well. It's a set of 3 cross 3 matrix such that Aij belongs to 0 and 1 for all ij belonging to 1 to 3. It means it's talking about a matrix whose entries are or elements are 0 and 1, right? So how many matrices will be there? Of course 2 to the power 9, because at every place we'll have two choice. For example, you can have 0 1 0, 0 0 1, 1 1 1. This is one such matrix. If an identity matrix the part of this set, even all can be null, or all can be 1 1 1 1 1 1 1 1 1. So for every position, let's say if I take, so we have 1 2 3 4 5 6 7 8 9. So in total I have got 9 particular locations, and at every location I have two choice, either it will be 0 or 1. Similarly 0 1 and so on and so forth. So in total we have to do the power 9 choices of matrices now, and that will come to be 5 1 2, right? So now the question is, among these 512 matrices, how many of them are invertible? Now all of you know, for a matrix M to be invertible, like for M inverse to exist, we must have that of M non-zero. Okay, so matrix will be non-singular. It is better to directly find the number of matrices in this set which is singular first. So let's say number of matrices M whose that is 0. Now why this is a better way instead of directly finding non-zero matrices is because of we have a definite clue of under what circumstances the determinant of a 3 cross 3 matrix will be 0. Of course that will be 0 under 3 fundamental circumstances. One is if all the rows are equal, then you can feel the volume of parallelepiped formed by them will be 0. Or when 2 of the rows are equal, any 2 rows. So just for the sake of understanding, I am giving you one particular example. Or is there any other case where still the parallelepiped is spanned by these 3 vectors represented by rows will give a 0 volume? Yeah, it's possible if one vector is some linear combination of other two. So maybe R1 is some R2 plus lambda times of R3. So under this configuration, definitely that of M will be 0. Is there any possibilities? Of course no. So I know for that M to be 0, for a 3 cross 3, we can have 3 fundamental possibilities. Either all the 3 rows are equal, or 2 of them are equal, third is not equal, or all 3 are distinct, but the third one can be written as linear combination of first 2. Okay, so equipped with these ideas, let's approach the problem by case making. I think it will be a better idea to give you, like one sample example from each of them. So if all of them are equal, it's obviously 1 1 1 1 1 1. If 2 of them are equal, maybe 1 0 1 1 0 1, and you can freely select the third one, right? If no 2 of them are equal, so maybe 1 0 0 0 1 0 and then 1 1 0. So you all the 3 rows are distinct, R1 R2 R3, but still it's that of this matrix M is 0. The reason is obvious because you can see the third row is linear combination of the first 2. R3 is nothing but R1 plus R2. So there will be no volume of the parallelepiped, because what you are getting is physically volume will be 0 as it will become coplanar. All these 3 vectors are coplanar because 1 1 1 can be produced by 1 0 0 plus 0 1 0. So in 3D plane, 1 1 1 is nothing but linear combination of these 2 vectors. Okay. So I hope the idea is clear. So very happily now we can do case making. Please be alert while you're doing case making, so be sure we don't leave any case. So let's take case 1 when every row is identical, right? So when R1 equals R2 equals R3. So clearly how many choices are there for the first row? Because whatever will come on the first row, that will be just copy pasted for the second and third. So for second and third we have no choice. In fact, choice is locked. For the first one we have two independent choice. Similarly we have two choice. Let's say we keep 0 0 0, and the second and third will be same 0 0 0 or 0 1 0 1 1 1, whatever. So we'll have two key choices and all the three rows are equal. Of course this also includes null matrix like 0 0 0 0 0 0 0 0 0. So there is no restrictions I am keeping on the first row. Let's move to the second row when two of them are equal. So let's say when row 1 and row 2 is equal and third is not equal. Either of them. Under this condition, first I have to select which 2 is equal. So 3C2, whether R1 R2 or R2 R3 or R1 R3. Now once I have selected, let's say R1 R2 is equal. So how many choices is there for R1 and R2? Clearly we have two cube choice. This also includes 0 vector. 0 0 0 is also a member of this. So let's say for example if I take 0 0 0, so second is automatically locked with 0 0 0. Now what about third? In third I can put any combination, any of the 7 remaining options except 0 0 0. So maybe 0 0 1 I can put 1 1 1 1 0 1 and so on and so forth. But except 0 0 0 is not allowed. So here we have 8 choice, here we have no choice, and here we have 7 choice, because you can't put the choice which is available at the first option. I hope it is clear. So hence we'll have for the last R3 we have 2 cube minus 1 choice. So first one is 8. Second case is giving me 3 into 8 into 7, which is 168 possibilities. Now let's come to the third case, in the most important case, when one row is linear combination of other two. Okay. Now when one row is linear combination of other two, under this condition, since I have already exhausted 2 rows equal and 3 rows equal, so here I am assuming all these 3 rows are distinct. No 2 of them is equal. Right? So R1, R2, R3 are distinct. Now it's worth noting that if, since the entries of these matrices is 0 to 1, so if any row has to be a linear combination of other two, what are the possibilities? Let's say for the first row if I keep 0 1 1, for the second if I keep 0 1 0. So what are the possibilities for third to have that equals 0 if they are distinct? So clearly I can take R1, multiply the second row with some factor, let's say 1 2 minus 1 3 or whatever, so that to produce the third one. Clearly if I'm multiplying with, let's say, any number apart from 1, so if I replace R3 as R1 plus lambda R2, where lambda is not 1, then what will happen? The element will not be from 0 comma 1. Why? Because region is clear. Let's say multiply with 2, so this will give 0. 1 plus 2 will become 3, and this is still 1. So 3 is not the member of that society. What if I multiply with minus 1? So if it is 0 0, it will still be 0. 1 minus 1 will make 0, and 1 in this is 0. So that's fine, right? So if I subtract both of them, it feels okay. So the linear combination. So one thing I know, like if mod lambda is not equals 1, so lambda possibilities can be either 1 or minus 1. Apart from that, I can't put any possibilities until this is 0 0 0. So let's say we have 0 1 0 0 0 0. Then you are writing R3 as R1 plus even 3 times R2. And then your logic will be, yeah, it will work because it will still be 0 1 0. But that is already defended because 2 rows equal case have. So the takeaway is any linear combination of the third row has to be simply the sum of the first 2 rows. Okay. In general, difference will also not work. So lambda minus 1 is not necessary always. Why? Because I can select 0 1 0 0 1 1, and if I subtract we'll get 0 0 minus 1. So that's not possible. Okay. So for the linear combination, the third row must be R1 plus R2. So lambda must be 1. And that gives the only possibilities here for linear combination because of the huge guardianship is one row must be simply sum of that. This, if you want, you can prove also as a linear dependency of the vector in a very simplest way. So you take a vector v1, v2, v3, have these row vectors, multiply with x, y, g, and prove that this is 0. If and only if x plus y plus z is 0. If that happens, then they are mutually dependent sets of vectors. Okay, anyway, so now moving forwards with this idea, I can investigate case number 3. So since each row is unique and one of the rows is 0 row. Now the problem here is, suppose if one of the row becomes 0 row, right? Let's say 0, 0, 0, and we have 1, 0, 1, and third is 1, 1, 1. So still that will be 0, right? So even if it is not a linear combination, but since one vector itself is dying, so that was another case where that can die, is one vector itself becomes a null vector, which I have left actually. Okay, so we have 3 possibility, and 4th possibility of course is when one of the rows is 0, because then of course we have only 2 vectors which will span a plane, right, which will make a plane. So hence I am segregating this and discriminating this into different criteria. So we have one case when one of the vector is 0, other case when none of Ri is 0. Okay, so in this case how many possibilities will be there? Since we know each row is unique, because for 2 equal and 3 equal we have already considered. So let's say if it is 0, 0, 0, for the second vector, how many choice we are having? We have 2 cube minus 1 choice. Because out of 8, 0, 0, 0 I can't put in the second. Now for the third one, again we have 2 cube minus 2 choice. Because once I have kept 0, 0, 0 over the first one, I can't use for the second one, and similarly I can't use first 2 for the third one. Okay, so with 0, 0, 0 in the first row, we'll have 8 into 7 possibilities. Now of course 0, 0, 0 can be the member of first row, second row, or third row. So we have 3 into 8 into 7. Sorry. So if 0, 0, 0 in the first row, for the second one I can't use the first, so we have 2 cube minus 1 possibilities. For the third one I can't use the first 2, so 2 cube minus 2 possibilities. So in total we have 7 into 6 for the first 2 row, and for the first row it can come at first place, second or third place, so we have 3 possibilities. So in total we have 126 possibilities, and remember this is when one of the vector is died. Now let's take the case when none of the vectors is 0 and all 3 are distinct. So now it has to be linear combination. So again, to get a feel and make a strong subcase, we can give example. Let's say we have 1, 0, 0. And what are the possibilities for the second one? Of course I can't put 1, 1, 1. Why? Because now the third one, it has to be different from the first row, right? And moreover it has to be linear combination now. So if it is linear combination, the only way 1 and 1 will be present is if we'll add them, so 2, 1, 1. That's not the member of the society. Of course it will subtract, we'll get 0, minus 1, minus 1. So that's also not valid. Clear? So once I have kept 1 at the first place, I'm not allowed to keep 1 for the second row at the corresponding place. So we have frozen case for the first number of the second row. What about at 0 and 0 place? Of course I can put 1 and 1. If you do so, the third will become 1, 1, 1, and that's all 3 are different and it's a valid combination. Let's come to the linear combination case, and it's really technical, and that's the most clever part of this question. Now what are the possibilities for linear combination case? Either the first row will have exactly 1, 1, or 2, 1, or 3, 1. Now if it is having 3, 1, then clearly the second row has to be frozen with 0, 0, 0, and the third will be simply sum of first 2 row as a linear combination, which I discussed. So this is not possible because 2 rows same are cases was already considered before. Okay, now what we can do is we can incorporate both of this and very smartly count both of this together. Of course, you can even make cases here, because first row is having exactly 1 1. The second row you can take one case when exactly 1 1 is there or exactly 2 1 is there. Similarly here you can see like the second will be frozen with 0 0 1, because you can't put 1 in place of 1, it will add up to 2, and at 0 you have no choice of keeping 0, because again it will become 0 0 0, which is already considered in the first case. Okay, so this will also be frozen cases. So both basically we can count very smartly. So let's say first row is having 1 0 0, exactly 1 1. And how many choices there at this place? You don't have a choice, so it is locked with only one choice, 0. Now at this place we have two choice of 0 and 1. Similarly at this place we have got two choice of 0 and 1. Of course these twos are distinct, right? So let's say if it's 1 0 0, second is 0 0 1. And then the third will automatically be 1 0. But a smartness is there. In this fourth choice, there is one choice which makes second row 0 0 0. And that's also we have considered before, okay? When exactly one of the row is 0. That was the very smart point when we segregated this in the very beginning. So for the second one, we don't have 4 choice, rather 3 choice, because 0 0 0 cannot be the member for the second. Now what about the third row? Third row is uniquely fixed. Why? Because let's say if you have 1 0 0 0 0 1, you don't have a choice for the third, just have to add this. That's the only way they will be distinct. Clear? And it has to be a distinct vector. The reason is very obvious, because at the first place I am keeping 1, so this is fundamentally I vector, and this is k vector. So this is, like I plus k combination. So it's definitely different, right? So we have I over here, k over here, and I plus k is oriented in different directions. So these three are different vectors. Because if the x component is different, of course the vectors will be different. Right? In this sense, overall y and z also we have to incorporate. Anyway, so how many cases are there? For the second we have 3 choice. Okay, so with 1 0 0 at the first place we have 3 choice. Now of course 1 0 0 can move to either second place or third place. So for 1 0 0 we'll have 3c1 choice as a whole. Now internal arrangement of 1 0 0. So 1 0 0 itself can internally arrange in 3 factorial by 2 factorial. Okay, so which is giving us 3 into 3 into 3, which is 27 cases. Now just you have to cross check once. In this 27 cases, have we missed anything? Okay, what about the case when we have 2 1s in the first row? So is this already incorporated? Let's check it. So let's say we have 1 0 0 and 0 1 1. Right, so that will give 1 1 1. Okay, so if you want 2 1 in any one of the rows, let's say if you want 1 1 0 over here, so we must have kept 0 0, and let's say 1 we can't keep, so we don't have a choice here now, right? Because to produce 1 1 from the linear combination of first 2 row, clearly 2 zeros must be there, and if I'm keeping 1 1 over there, you don't have a choice, okay, because nothing will work. So hence we have missed the cases when we have exactly 1 1 0 in the problem. Okay, so we'll count this separately. So when we have 2 1 and single 0, then we don't have a choice here. We have to keep 0, we have to keep 0, and we need to keep 1, and that will give you again the frozen choice of 1 1 1. So in this case, for a particular choice of 1 1 0, we have only unique choice. So for this unique choice, you have 1 1 1 choice. Now 1 1 0 itself can permutate along the rows in 3 ways. So 3c1, it can come to the first row or second or third row. Now once it is in the first row, still 1 1 0 can have 3 possibilities. It can be 1 1 0 or 1 0 1 or 0 1 1. Okay, so first this row can interchange in 3c1 ways, and internal arrangement is still 3C1 wedge. So hence total we have 9 possibilities. Okay, now we are done because we have taken a case when we have exactly 1 in the first row or exactly 2 1 in the first row, right? Exactly 3 1 is already discarded, I have told, because 2 rows will become a same. Now some of you might feel like, sir, still 20. So in the last case we have 29 plus, so in the last case we have 27 plus 9, which is 36 possibilities. Now if you have a doubt, sir, where is the case when we have exactly 2 1s in the second row? Okay, so of course we have already found this, because when I am taking that the rows can interchange among themselves in 3 possibilities, so all these permutations of row is also taken care of. Okay, so now just we'll add all these answers, and adding all these answers is giving us 8, the first case 2q, plus 168 plus 126 plus 36, which is 330. And remember, this 338 is the answer for that a equals 0. What we want, that a non-zero. The total possibilities was 2 to the power 9, which is 512. So hence number of matrices, which is non-singular or invertible, it is 512 minus 338, which will give you 4, 6, 164. And this is the answer for the problem. I hope you have enjoyed this, and now you can solve all the previous 5 years problem, because in the last year of JEE questions they have given comparatively very easier cases, because the number of zeros in one was also fixed. Their question was find the number of invertible matrices if there are exactly 2 zeros in the system and rest all are 1, or you can do if there are exactly like 2 1s in the system and rest all are 0. So the first question will be little bit okay, the second question is really easy. Okay, so this is how you interact with the basic ideas of permutation in the matrices. I'll come with more video of this type. I think like one cascade of problem I should solve based on problems of this model. That will give you confidence for the upcoming JEE. Thank you. Have a good day, and please do subscribe.